Hey everyone, how's it going? We are finishing up our Unit 3 packet today by doing 3.5. I have adjusted 3.5, so you'll have to give me some leeway here. We're going to be crossing some stuff off and doing not as many examples and things like that, okay? So 3.5 is all about using these exponential and logarithmic models. However, what we're really going to focus on in 3.5 is just exponential growth and exponential decay. Okay, so objectives here, we're kind of only focusing on just this one, where we're looking at exponential growth. My pen is really jumpy today, so I apologize. And exponential decay to model and solve real life problems. So growth and decay, we hit it hard in Algebra 2. You also learned it in Algebra 1. So this should look fairly familiar, but we're going to review it first and then do some problems, and it shouldn't take very long, I don't think. Okay, so out of these 5 most common models using either exponential or logs, we're only focusing on 1 and 2. Okay. So the first one that we're focusing on is exponential growth. So this means I'm increasing from left to right. So it's doing something like this. Okay. And I have my asymptote is there on the x-axis. Okay, so for 1, if b, whatever I'm multiplying by x, if it's positive, then I'm increasing from left to right. Okay, so, and then number 2, if it's negative, then I'm going to be decreasing from left to right. And those are really the only 2 that I want to focus on in this lesson, just because we don't really have time to dig deep into these other ones, and I don't want to just scratch the surface if we're not going to get to really look at them. So all we're going to do is we're going to look at some word problems that are involving growth and decay. You are probably going to want a calculator in this lesson. It's going to be very helpful for you. So we're going to look at example 1. And it says estimates of the world's population growth in millions from 1998 to 2007 are shown in the table, right? So this is 5,930 million, so 5.9 billion, okay? So everything adds a million onto the end of it. Here's the exponential growth model that is the model where this data came from. P is the population in millions, right here. And t equals 8 represents 1998. So notice that t is from 8 to 17, where 17 is 2007. Okay, compare the values given by the model with the estimates shown in the table. According to this model, when will the world population reach 6.8 billion? Okay, so easiest way to do this, at least I believe the easiest way to do this, is to graph this equation, this guy right here, in your calculator, and then plug in, right, the values. So make sure that we are remembering that this is 8, right, 9, 10, blah, 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 blah. Okay, and I want to know when it's going to reach 6.8 billion. So that's going to be like 6,008 something something, right? I'm looking for like 6,800 or whatever, because it's 6.8 billion and this is 6,800 million, which is the same thing as 6.8 billion. Okay, so let's pull up our graphing calculator and graph this and then see what we get. Okay, so I'm going to pull out my calculator and I'm going to clear this out. And I'm going to go ahead and enter the equation. So 5,400 e to the 0.011852 x. Yep. Okay, now I don't really care what the graph looks like, so I'm going to go straight to the table because that's going to be the easiest way for me to see these values. So I'm going to go second table or second graph, and here's the table. And I know that this table starts at 8, so there's my 8. And I want to go from 8 to 17. So there we go, 8 to 17. And then I'm just going to go ahead and fill in those numbers, and I'm just going to round. Okay, so notice that, so when I round, let's think about this for a second, right? If I have like 6.2 people, not million or anything, just 6.2 people, that 0.2 person isn't a whole person, right? So it's how many people do you have? So it would just be 6. So even if I had like 6.9, it would still only be 6 people. So because we're talking about people here, all of these are going to round down. Okay, so I'm going to come here and I'm going to fill in the numbers. 5937. So go ahead and fill in those numbers, and I'm going to do that here on my end as well. Okay, so here we are. I filled in the numbers. Boom, right? All done. Now I have to do the second part. According to this, so it looks like the population and the equation are very, very close to each other. It says, according to this model, when will the world population reach 6.8 billion? So I'm going to take this equation and I'm going to set it equal to 6,800 because that is 6.8 billion. And then I get 5,400. My pin is so jumpy. E to the 0.011852 x, or t, sorry. My bad, it's a t. Okay, I'm going to go ahead and start by getting rid of this 5,400 by dividing it to both sides. When I divide, I'm going to keep the number on my screen, but just for the sake of notes, I'm going to write it's 1.259 blah, 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 blah. And that's approximately e to the 0.011852. Excuse me, 2 t. Okay. All right, and I'm trying to solve for t. I want to know what year is the population going to reach. So I need to get rid of this e. So I'm going to take the natural log of both sides. Okay, if I take the natural log of both sides, I get the natural log of 1.259, which again, the reason I'm putting the dot, dot, dot here, I'm not rounding that in my calculator. I'm leaving that answer in the screen of my calculator. And if that's not making sense, what I mean on that, then just ask me. But it's really important that you're not rounding those numbers, okay? Okay. And then the last step is I can just divide. So I'm going to have to find room. So I'm going to take the natural log of 1.259, whatever that number is, again, right? I actually take the natural log and I'm going to divide it by 0.011852. And that is approximately t. So if I do that in my calculator, so I'm going to show you how this looks when I do it in my calculator. Okay, so I'm going to start with 6,800 divided by 5,400. Okay, so there's that number that I get. And I'm just going to take the natural log, and I'm going to go second answer, ANS, it's above the negative sign. Okay, so I'm going to take the natural log of that, and I'm going to divide that by 0.011852. And I get 19.450. So T is approximately, there we go, 19.45 years. Don't forget units. Okay, that's great, but that doesn't make sense. I want to actually know what year, right? Well, 17 is the year 2007. So then 18 would be 2008. 19 would be 2009. So like halfway through 2009. So remember, we got to always write a sentence. So during 2009, the population will reach, so jumpy, 6.8 billion. There it is. That's it. (2009). So hopefully we feel good about that. Yeah, fun stuff. Woohoo. We're just going to do example 2 and 3 as well, and then we'll be done. So let's go ahead and scroll down and look at example 2. Okay, so example 2 says, in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. Okay, well, if it's exponential growth, I know it's going to be y is equal to a times e to the bx. Because exponential decay, this would be a negative, okay? After 2 days, there are 100 flies, and after 4 days, there are 300 flies. So I'm going to write an equation here. I'm going to write there is 100 flies, so y, right? Don't know how many I'm starting with. Don't know what I'm increasing by, but I know that x is 2 days. So after 2 days, there's 100 flies. And after 4 days, there's 300 flies. So 300 equals a times e would be times 4. Okay, and the question is how many flies will there be after 5 days? So I'm just going to rewrite this equation just so that it doesn't look as weird. Okay, so it's a times e to the 2b, right? And then this is 300 equals a times e to the 4b. Okay, the only thing that is common in both of these equations is my a. It's the only thing that's common. So I'm going to solve both of these equations for a. So I'm going to divide this side by e to the 2b, right? Divide by e to the 2b. So I get 100 over e to the 2b equals a. Here I'm going to divide by e to the 4b, so I get 300 divided by e to the 4b equals a. Okay, so if they're both a, right, if this is a and this is a, then they're the same thing because a is equal to a. So I can then go ahead and say that 100 over e to the 2b equals 300 over e to the 4b, right? Because they are the same thing, they're both a. So I'm going to cross multiply because I'm trying to get everything onto one line and I don't like the fractions. Okay, and then I have 200. Oops, sorry, I don't know where I got the 200. Definitely a 3. 300 e to the 2b. And I'm going to keep solving. 100 divided by 300 is 3. And then e to the 2b, well, let's just do it this first. So e to the 4b equals 3e to the 2b. So I just divided both sides by 100. Now I'm going to divide both sides by 2b. I actually think that this is better. Come up here, so I'm running out of room. Right, smaller than I did, right? So if I divide both sides by e to the 2b, so e, well, if I have 4 b's on top and 2 b's on bottom, I'm left with 2 b's. I have e to the 2b on the left equals 3. Now this is something that we know how to solve, right? I want to get rid of that e. So the way to get rid of the e is to take the natural log of both sides. So I have the natural log of e to the 2b equals the natural log of 3, which leaves me 2b equals the natural log of 3. So b is equal to the natural log of 3 divided by 2. So I'm going to take this and I'm going to do it on my calculator. So natural log of 3 divided by 2. And I get about 0.5493. Let's do 5493 to be a little bit more accurate. So I get B is approximately 0.5493. Okay, that's great. I found what B is. I found what this number right here is, right? But I want to know also what A is in order to write the equation. So I'm going to take my B value, and I'm going to take my exact B value, and I'm going to plug it in for one of these two equations. And I like this one because the numbers are smaller. So I'm going to take 100 over e to the 2 times b. Well, b is that 0.5493. It's really hard to write small, so hopefully you guys can read what I'm writing here. Okay, so this is what I'm going to do. I'm going to multiply this number by 2, right? Then I'm going to take e to this number. So I'm actually doing the bottom first. There you go. I get 3. And then, so the bottom is 3. So I get 100 over 3. And now this is not something that I can simplify, nor do I want to. So I'm just going to leave it. So my equation is y equals a is 100 over 3 times e to the 0.5493x. So there is my equation. That's not a new process. We've done that, not necessarily in this class, but we've looked at that a lot in other classes. And then the last part just says, how many flies will there be after 5 days? So I'm just going to plug in 5. Okay, so y is equal to 100 over 3 e to the 0.5493 times 5, And if I use my handy dandy calculator, I'm going to get about 519 flies. So in order to find out how many flies there are on the 5th day, I needed to write the equation so that I could use the equation to find it. Hopefully we feel good about that. Please make sure you reach out. If you don't, we just have one more example. It has 2 parts, but only one more example left, and then we're going to be done with these notes. So, how do I do that? There we go. My pen doesn't like me today. There we go. So let's clear this and scroll down. Okay, so really quickly, just a quick excerpt about carbon-14. So I'll read it, but it says in living organic material, the ratio of carbon-14 to the ratio of carbon-14 to the ratio of carbon-12 is about 1 to 10 to the 12th. So what that means is, like, when a living thing dies, it's the carbon-12 stays the same, but the carbon-14 starts to decrease. And it has a half-life of 5,715 years. So every 5,715 years, the amount of carbon-14 in the living thing cuts in half. Okay, so that's how we're able to estimate the age of things, like fossils and things like that, is using the carbon-14 versus the carbon-12. Okay, and then this is the equation that we can use to figure out how old something is. Okay, so we're going to be using this equation a lot in talking about how old things are and how we can figure out how old fossils are and things like that. So we're going to just look at example A here. All right, so let's look. It says the ratio of carbon-14 to carbon-12 in a newly discovered fossil is R equals 1 over 10 to the 13th. Estimate its age. So if I scroll up just a little bit, there we go. Okay, I'm given what R is, right? R is this. So I'm going to take what R is equal to, and I'm going to set it equal to 1 over 10 to the 12th e to the negative 8245. Okay. I don't really like these fractions going on, so let's get rid of this fraction. I'm going to multiply, let's change color here. I'm going to multiply both sides by 10 to the 12th. I have to get that e by itself before I can take a log. So that's kind of what I'm doing here. And then these guys cancel. And then if I do this off to the side, let's do it over here. 10 to the 12th on top and 10 to the 13th on bottom leaves me 1 over 10 to the 1. Okay, so this becomes 1 over 10 equals e to the negative t over 8245. Okay, now I can take the natural log of both sides. So the natural log of 1 over 10 equals the natural log of e to the negative t over 8245. Right, so these can cancel. I get the natural log of 1 over 10 equals negative t divided by 8245. Okay, so I can also write this negative down on the bottom and then make this a positive, and I'm going to do that because now all I have to do is multiply by negative 8,245, to both sides. And that's just going to give me t. Okay, so then t is approximately, let's bring up our calculator again. Maybe, there we go. So I have natural log of 1/10, or you can just do 0.1. Okay, there it is. And I'm going to multiply this by negative 8,245. So I get 18,984.814. So t is about, 18,984.814 years. So that's how old this fossil is. It's, almost 19,000 years old. And I can tell that just by the amount of carbon-14 that remains in the fossil. So that's pretty cool, right? Fancy. Let's look at B, and then that'll be our last problem. Okay, so B says a fossil contains 20% of the carbon-14 that the item would have originally contained. Estimate the age of the fossil. Okay, so what I'm going to do is I have to find out what 20% of that is. So 20% of, and then carbon-14 that's in the, blah, 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 blah. The carbon-14 that's in the fossil that would have originally been in the fossil is my 1/10 to the 12th. Okay, so I'm going to make that 20% a decimal, so 0.2 times 1/10 to the 12th. And I just get 0.2/10 to the 12th. So that is how much carbon-14 is left in the fossil. Okay, so that's going to be my right-hand side, so 0.20/10 to the 12th equals, and then that equation that was given to us, 1/10 to the 12th, e to the negative t over 8,245. Okay, again, I am going to multiply both sides by 10/12. Not 10/12, sorry, 10 to the 12th. Excuse me, these cancel. And actually, these cancel too. So that's exciting. And I get 0.20 equals e to the negative t over 8,245. I'm going to take the natural log of both sides. Hopefully we're getting to the point where you can kind of start skipping some of these steps that I'm writing because you just know what's going to happen. Okay, here the natural log and the e cancel, and I get natural log of 0.20 equals negative t over 8,245. Okay, again, I'm going to make the lower, the denominator negative and the numerator positive, so that all I have to do is multiply by that 8,245, multiplied by the negative, 8,245, I wrote 54. That's how you know it's been a long day, right? 8,245. There we go. And so when I enter this into my calculator, let's do it. Let's go. I have the natural log of 0.2 times negative 8,245, and I get about 13,269.816 years. So this fossil is about 13,000. Oops. 269.816 years old. So just lots of work here on these problems with natural log and E and growth and decay and all that fun stuff. Minimal practice problems on this today because I took out most of section 3.5. But if you have any questions, let me know. Otherwise, this is it for 3.5. This is it for topic 3. We're almost done. If you have any questions or any concerns, or if you need anything, reach out. Otherwise, we'll see you soon.